Alright, today I just wanted to take a little diversion here and do a video, and this is actually in response to a question that I received on one of my videos. Recently I was doing some analysis of amplifiers, and I was referring to the taking of differential measurements, and I received a question, actually two questions, about what it means to take a differential measurement, and why you just can't take an oscilloscope and take the ground connector and the probe tip and just probe anywhere to find out what voltages exist across certain components. And you just can't do that, actually, and I'm going to explain to you why, and I'm going to explain to you the dangers involved. But typically when you're, and I realize the schematic here is very small and hard to see, and that's okay, I'm going to draw some larger things here in a minute. But typically when you're probing around an electronic device, and particularly with me, I deal with audio devices such as amplifiers, and that's what you're looking at here is a schematic of an amplifier. Typically when you have your oscilloscope, the oscilloscope has a probe tip, and it has a ground connector, which is usually an alligator clip like that. And typically you would take this alligator clip and find a chassis ground. It's hard to see, but some place where you can attach that to the chassis, and usually the chassis is also somewhere along the line earth grounded. And so you would tie your alligator clip there, and then you can start probing around anywhere you want to, and the voltage measurements that you're getting are relative to ground. However, there are times that you want to actually measure the voltage across a certain component, and that's what I was doing the other day. And in other words, not relative to earth ground, relative to two sides of a component. And an example of what I was doing the other day is I wanted to get a picture of the current flowing through the emitter of a transistor. So I wanted to take my oscilloscope, and I wanted to see the waveform of the voltage that's being dropped across that resistor, because that's a picture of the current that's flowing through the emitter. However, neither of these points here are earth grounded. So I cannot just take an ordinary oscilloscope and just go like that, or like that. You cannot do that. You're likely to damage the oscilloscope, perhaps, and or fry the circuit. And there is a reason for that, and that's the essence of this video. Now, I will say this: if you have a battery-powered oscilloscope or battery-powered digital voltmeter, you certainly can do that. Okay, you can take the probes of a battery-powered voltmeter or battery-powered oscilloscope, and you can take a differential measurement. This is what a differential measurement means, basically the difference between one side of a component and the other. That's differential, not relative to earth ground. So you can do that with battery power, but you cannot do that with a plug-in type oscilloscope. Well, actually you can. There is a technique you can use, but it's not. You have to know what that technique is. You have to use both probes, and you have to subtract the signals. And I'm going to give you an example of that coming up. But you cannot do that, or you're going to damage something. So, in order to demonstrate what I'm referring to, I'm going to come up with a real simple circuit, and you're looking at it right here. I am going to apply a 1 kilohertz sine wave at 9 volts RMS across a load of 3 identical resistors. So what we're going to get is, because there's 3 identical resistors, it's going to carve up that 9 volts into thirds. So 3 volts will be dropped by each resistor. Now, this source here, my voltage source, is earth grounded. So the negative lead from that is earth grounded. And then there's the positive going up. So we should see 3 volts dropped on each resistor. So if we were to measure with an oscilloscope, okay, so on our oscilloscope we tie our alligator clip in right there, and we take our probe, and if we were to probe it across the bottom resistor here, we'd get 3 volts. If we were to probe it here, we'd get 6 volts, and probe it there's our full 9 volts. That kind of measurement we can take, no problem, because the alligator clip, okay, on the oscilloscope is tied into earth ground, no problem at all. But what if we wanted to do a differential measurement across this resistor right here? Okay, and you could see that if we were to take a voltmeter and put one lead there and one lead there, we would get a 3 volt drop. We would see just 3 volts. Okay, so what if we wanted to do that with an oscilloscope? We wanted to get a picture of the current flowing through that particular component. Well, we wouldn't necessarily get that if we were tied into earth ground. What we'd be seeing, if we probed up here with an oscilloscope, we'd be seeing 6 volts. We wouldn't be seeing a reflection of the current flowing through that resistor alone. We'd be seeing the current flowing through that resistor and everything else below it. There could be other circuitry down here, who knows. We want a differential measurement across that. In the same way, we want a differential measurement across this emitter resistor. So how do we do that? Now, if I were to use the oscilloscope and I were to take a differential measurement across that resistor right there, here's what would happen. There would be a problem. Remember, this lead of the oscilloscope is earth grounded. So in essence, what I'd be doing is I'd be taking this point here and I'd be bypassing that resistor and grounding it. So this resistor would no longer even be in the circuit. So what we would have is the full 9 volts being only dropped across 2 resistors. So we'd end up getting a reading of 4.5 volts because I've effectively short-circuited the bottom of that resistor. So that wouldn't be accurate. And that's a problem in a couple of ways. Number one, I'm not getting an accurate measurement. Number two, I've just short-circuited part of my circuit. Now, this is a simple circuit, but what if you were short-circuiting a critical part of a power amplifier? Who knows what would happen? You could have, as soon as you short this point, you could have a mess of current running, all of a sudden running through these components, and it would fry everything in its path. Who knows? All kinds of bad things can happen. So, how do we take differential measurements? Well, first of all, I'm going to go ahead and demonstrate exactly what I just showed you in real life here with my 3 resistors. So, back out here. So there's my voltage source, audio generator, and here are my 3 resistors. Let me get rid of these probes here. So my top resistor here, followed by my middle, followed by my last resistor there that's hooked up to ground, and my source is earth grounded. So what should we see across each resistor? Well, let's go ahead and turn this thing on, and I'm certainly in no hurry to doing this, so it's gonna take some time here, but again, I never make videos for those afflicted with ADD. Plenty of other hyperactive videos you can watch if you need instant answers. So I've hooked up my voltmeter. I'm going to go ahead and turn it on volts AC. Let's go ahead and turn on my source here, and I'm going to adjust for 9 volts RMS across 8.9999 whatever. Okay, so now we have, okay, so there's our circuit. Now let's start out, before we go to the oscilloscope, let's just start out using the DVM, the digital voltmeter, and take some measurements. So I just took a measurement of 9 volts here because I have a 9 volt RMS source. Okay, so let me take the positive lead of the probe and let's go down to the next resistor. And of course I have 6 volts. Completely expected, right? Now let's probe right here. Let's move my lead over to the final resistor. And of course I have 3 volts. Now let's take a differential measurement. We can do that because we have a battery powered oscilloscope, a battery powered DVM. That's nothing on this DVM is referenced to earth ground, so I'm not going to short anything out. So let's go ahead and probe here and here. And what do we expect to get? Well, every resistor drops 3 volts. We expect 3 volts. So let me go ahead and probe across that middle resistor. Got me kind of a mess here, but okay, there we go. There's our differential measurement. 3 volts. Okay, we've just taken the differential measurement, a measurement not referenced to earth ground, a measurement that's across a component in the middle of a circuit. No problem, right? Now, let's create a problem. Let's do the same thing with the oscilloscope. Okay, I'm going to remove my DVM out of the loop completely. And we go ahead and get that oscilloscope. I should have had. Okay, so have the oscilloscope on, and let's start by verifying the same things we verified with the DVM. I'm going to start with the oscilloscope's ground alligator, and I'm going to go ahead and tie right into earth ground. So I'm doing this the proper way. And then I'm going to probe. I'm going to start out with the oscilloscope, and we're going to start up here at the top of the circuit, which is where the probe is. And as you can see, we have 8.98 volts, essentially 9 volts RMS, exactly what the DVM told us. And let's go ahead and probe down, set the camera down one rung lower. Alright, so you can see the waveform got a little smaller there. So now we're probing right here where we measured 6 volts with the DVM, and of course we've got 6 volts RMS by the scope. And let's go down to our bottom resistor. Let's just go through the exercise here. Of course we should expect to see 3 volts. And we see 3 volts. Okay, so far so good. The oscilloscope is perfectly consistent with the DVM, as it should be. Now, let's take our differential measurement. Okay, let's take the negative or the ground lead of the probe of the scope and pop it right here, and we'll take the probe of the scope and pop it right there, and let's see what happens. I'm going to set the camera down and do that. Now, we expected, in the DVM, we saw 3 volts, as we should have expected, because every resistor drops 3 volts. Okay, so I have the ground lead of the oscilloscope over here, this yellow guy, yellow alligator, on one side of the resistor, and I have the probe on the other. There's our signal, and what do we see? We see 4.5 volts, not the 3 we expected. And already explained why. Why? Because we have effectively, with the ground lead of the probe of the scope, we have effectively taken that point to earth ground. So there's only 2 resistors in the circuit to drop 9 volts, so each of them has to drop 4.5 volts. We've shorted out the circuit by taking a differential measurement with an oscilloscope. Bad news, in this simple circuit it's no big deal. But extremely bad news when you're inside of a high-powered audio amplifier or a tube amplifier. Oh God, God knows what would happen. Bad news. So, having created this problem, let's talk about solutions. What are the ways we can take differential measurements properly without effectively blowing up our circuit, which is what I just did in this simulation. How do we do it? Well, there's a couple ways. And of course we can use a DVM to measure volts RMS, but I want to see a picture of my need is to see a depiction of that, okay, that waveform. I want to see what it looks like. That becomes important in certain parts of audio diagnosis and design. So I need an oscilloscope. Okay, so solution number 1, we go ahead and revert. Alright, so there are several solutions to this, to taking differential measurements. One is the use of a battery-powered oscilloscope. An oscilloscope that does not plug in to the wall and hence is not referenced to earth ground. In the same way that you can use a battery-powered DVM to take measurements, you can use a battery-powered scope to take differential measurements. So that's what I have here. It's a little, very tiny thing, battery-powered scope. It's not the ultimate in accuracy, but a lot of times I don't need to take scientific grade measurements. I just need to look at a waveform and see how it changes and responds and so forth. So I've taken the probe of this battery-powered scope and I am taking a differential measurement across that resistor, the same way we just destroyed our circuit with the plug-in scope. Okay, and we got 4.5 volts with the plug-in scope because I shorted the circuit. However, as you can see on this scope, if you can see it, that little thing there, volts RMS, 2.88 volts RMS. So it's 3 volts. We are measuring 3 volts. This is doing the job and it's not shorting anything out. So that's solution 1, battery powered oscilloscope. Now if you need additional accuracy and you have to rely on a more expensive plug-in scope, there are solutions there as well. There's a couple of solutions. One is to, and I'll go over this real quick because I don't have this, you can purchase what are called differential probes. And it's a type of probe you plug into this scope. They're very, very expensive. That's why I don't have them. I hardly have the need for it. I don't need to buy them. But the differential probe is actually one probe you plug in, and you can look it up online. And there's a little box, and out of that box are 2 prongs, you know, just like that, so to speak, or 2 probes that come out of it. And you can take differential measurements with that. It essentially, even though it doesn't function this way, it essentially converts your measurements to like what the battery powered scope would do, and then from the battery powered scope back to the oscilloscope. It removes any reference to earth ground. But they're very expensive. I don't need them. I don't have them. However, there is a solution where we can use both probes, okay, channels 1 and 2 of our scope, to take differential measurements with each channel being referenced to earth ground. We go ahead and draw that. Okay, so here's what we're going to be doing. We're using 2 probes. Probe 1, we're going to attach the ground lead to earth ground as we should, and we're going to probe the bottom side of that resistor. And our second probe, same thing, it's going to be referenced to earth ground, and we're going to probe the top side, and we'll get 2 different signals. Okay, probe 2, that's probing the top side of that resistor, will give us a sine wave that is 6 volts RMS. 6 volts. Probe 1 on the bottom side, because we know that that resistor drops 3 volts, will give us a similar sine wave at 3 volts RMS. Okay, I still haven't taken a full differential measurement yet. I'm just measuring 2 different points in the circuit and getting 2 different sine waves. So in order to get a differential measurement, what I need to do is I need to do some math. I need to get our differential measurement. Sorry about my writing, it's always been bad. I need to take our reading from probe 1, I need to subtract from it our reading from probe 2. In other words, 6 volts minus 3 volts. And that'll give us our two things. That'll give us a sine wave, that's the difference between the two sine waves, because we're looking at it on a scope. And that sine wave ought to be 3 volts, just like we saw in the battery-powered scope. So that's, now, this is a math function. And we can do that on most scopes. There's different ways you can do it. Old-fashioned scopes, you can invert one channel and add it to the other. But here we have a math function, and this math function will allow us to subtract channel 2 from channel 1, or channel 1 from channel 2, etc. So let me go ahead and get that hooked up. Okay, here's what it looks like. Okay, so my yellow probe here is going to be equivalent to probe 2, and my blue probe here will be equivalent to probe 1, and there are the waveforms. And as you can see, probe 1 is a larger wave, higher amplitude than probe 1. And let's see here. Bear with me a second, I should have done this. So, oh, my voltage creeped up. Hold on a second. Okay. All right. So, our yellow waveform from probe 2 is at 6 volts RMS, right? And our blue waveform from probe 1 is at 3 volts RMS. Exactly what we should expect. Exactly what we should have expected, 6 and 3 volts. But I want to do the math to see the difference signal. Okay, so all I'm going to do is I'm going to hit the math button. Again, this is done differently on different scopes. And instantly, oh, there's some options here I've already set. Channel 1 minus channel 2. So this minus that. And we will get a waveform that depicts this subtracted from that. Blue subtracted from yellow. And that's our differential signal. And our differential signal comes in at 3 volts RMS. You can see that or not in the red. 2.97. And that's exactly what we should expect, and that's exactly what we got. That red waveform is effectively what we got by using the battery-powered scope. And I've done this without shorting anything out in the circuit, because both of my probes are referenced to earth ground. Now, sometimes that's just a real pain in the butt to go through this whole process with both probes and do the math function and all that. I just want a quick measure. I'm not worried about the nth degree of accuracy. I just need to see what the waveform looks like and get a rough idea what the voltage is and so forth. I'd rather just get out my battery-powered scope, hook it up, I'm good to go. Got my measurement in a couple seconds. This scope here, you got to turn on. You should let it warm up for 5 minutes before you use it. Then you got to get both probes hooked up, punch a bunch of buttons. Sometimes I want quicker than that, so that's why I'll use the battery-powered scope instead of the Tektronix. But if I want accuracy, I'll go with the Tektronix, or at least greater accuracy. So there you have it. That's what I mean by differential measurements, and that's the importance of using, or at least of knowing how to take them and not shorting something out in the circuit with a device that is earth grounded. I hope that helps. I hope that answered the questions that I received regarding that. The moral of the story is you just can't go probing around. Well, you shouldn't do this unless you know what you're doing anyway, but when you take measurements off a device, that little ground lead from the probe of your scope has to be connected to chassis somewhere, or at some point where you have a circuit ground that is also referenced to earth. If you go taking differential measurements, use a battery powered device or use this technique here, because again, taking differential measurements. You don't know what you're doing, you're going to end up shorting, literally shorting things out. It's like taking the copper wire of you know, it's like sticking a wire into this prong right here, which is earth ground of your plug, and just sticking it places in here. What do you think is going to happen? I'm just saying this just to tell you to be careful. So, okay. Thanks for watching again. I hope this was informative. I should have looked on YouTube to see if someone else had done the video about differential measurements with an explanation. I don't know. Maybe I'm just repeating. Maybe I'm just another in a host of umpteen videos doing this. But what the heck? I felt like doing it, and I hope it's a good contribution. Thanks for watching, and ciao.